Any questions about the most amazing lectures you've been listening or witnessing? Every single one was important. But today is an even more important one. The title, how should I say, the title will become apparent as we slosh through. During the previous lecture, we got to know the idea called the boundary layer theory. I'll sketch on the blackboard the ingredients. We assume a two-dimensional flow configuration. That means x versus y with those two velocity components, u and v, steady state. And by invoking those three equations, mass conservation, momentum in the x direction, momentum in the y direction, and subjecting them to the assumption that the flow region of interest is slender. That is, there is a wall here, and then there's a region of thickness delta and length L. So plus the assumption that the delta is considerably smaller than L, we arrived at the so-called boundary layer theory, which anticipates analytically the size of this delta. This delta turned out to be of the order of the length times the Reynolds number based on length to minus 1/2. And then, of course, we evaluated the scale of the skin friction coefficient, which is this force per unit area. And then in dimensionless form, we expressed it as the skin friction coefficient. This is the shear stress. This is the skin friction coefficient, dimensionless, which is of the order of the Reynolds number to minus 1/2. This sort of notation, I explained, is artificial. The non-dimensionalization is based on a unit of stress, which is not a stress, which was that dynamic pressure, 1/2 times rho times velocity squared, the velocity being the free stream velocity u infinity. But they're compact enough to make remembering easy. You see, that's the origin of the field. Okay, so that's a very brief review of the previous lecture. My plan today is to show you two ideas, the second of which is the next section in the book. But the first idea is kind of a, let's call it playing with this interface between the past and the present. The present being in my mind, because there's nothing newer in my thinking except what's occurring in my mind during the night. If you think about what's going on in this picture, meaning, I'm assuming you think, that is not a drawing, it is actually a flow or a movie. You can imagine a, let's call it a little packet of fluid, not a particle. I avoid that word, okay, because particle is the language of these people who pray to the altar of reductionism, also known as the invisible. It's, I like to say, the cigarette butt that you throw into the river. It's small, you see it, it floats, and it gets carried away. So this thing is, of course, going from left to right with this speed. And that speed is the speed of sweep, or sweeping, or of scraping the wall. Hand in hand with it, there is a time of sweep, the time it takes for this thing to get here. So the time of sweep is L over U infinity. What's interesting about the movie I'm describing is that because the fluid is viscous, its precedent, let's say, preceding particles get stuck to the wall partially, but they get piled on each other, and this little packet ends up here. You see? And now there's an observer who is stuck, or meaning stationary here. Let's say Drew here, and sees nothing except what's flashing in front of his eyes. And it seems from this point of view that the effect of viscosity, which has to do with rubbing against this wall, you can call it slowing the flow down, took this time to propagate itself. I'm talking about that effect of slowing the fluid down. It took this time to propagate to the distance delta, from the wall vertically to delta. So previously, we're writing on this particle. That's one frame of reference. Next, in the stationary frame of reference, this delta is the viscous penetration or propagation distance. Get it? Anyway, so that's a kind of slightly different language in which to translate the conclusions of the preceding lecture. To make this second point of view more clear, I decided to expose you to a problem that's in fact older than Prandtl. Remember, Prandtl was in 1904. In fact, he presented this idea of his at a conference, in a conference paper, very, very humbly, or very, I should say, on just 2 pages, part of a bigger paper that he was giving, almost afraid to say it. He was very young, in his 20s. That happens at your age. And in his environment, which was obviously Germany, the turn of the century, the intellectual activity in the university was truly, truly bubbling, and his cohort, his peers, made him realize that he had come up with something very different, which was this ability to solve the Navier-Stokes equations on the back of an envelope. The way he did it was not exactly on an envelope, but meaning later in subsequent papers. But you see, young individuals with ideas are fortunate if they are mingling with people who are intellectually alive and free, as opposed to others who are in fact already sedimented at the bottom of a dead lake. In academia, you find mostly the latter, especially today. So you're very young. Hang on to your wits, because they're the most precious things in the country, in fact. All right, so let's see a problem that was older. It is the following. Imagine a one-dimensional situation. That means a solid wall here and an infinite body of fluid in the vertical direction. The vertical direction is the only direction or dimension that you could measure with a ruler. We call it y. And the wall is solid. It's stationary. Therefore, if the wall were to move, and it will move very soon, but if it were to move to the right, then there is only one velocity component called u, on account of the fact that the fluid is viscous, and what's close to the wall will be entrained by the wall. And that is the beginning of the problem statement. The wall is solid, and at time t greater than 0, it starts moving to the right with the velocity u. So u is the value of little u at y equals 0. That is, in other words, the wall suddenly begins to move parallel to itself to the right. And once again, there was one of you standing here stationary. Who was that? Anyway, the previous you? Okay. You're still here. So from your point of view, the velocity distribution in the fluid is initially this way, meaning 0, even though the wall is moving to the right with a velocity u. But in time, a thicker and thicker layer of fluid feels the movement of the wall. So in time, this is what's happening. Clearly, nobody called it a boundary layer, but clearly, this is a time thickening boundary layer of a thickness. And the thickness in a drawing such as this one is the position, that is order of magnitude speaking, position of the knee in that curve. If the curve has only one knee, then that curve has one length scale, meaning the length scale of the drawing has to do with how sharp the knee. So in a drawing like this, the dimension of interest is delta, which is a function of time. And that is the problem. That can be solved this time on half of a back of an envelope using scale analysis. The two equations that I will invoke are mass conservation and momentum in the x direction, because there is no movement in the y direction. So let's see what we get for steady state. We get the du dx plus dv dy equals 0 for mass conservation. And for momentum, we get u du dx plus v du dy equals minus 1 over rho, and then the dp dx plus nu, and then d2u dx2 plus d2u dy2. A lot of stuff to copy from the textbook. These equations are available. These are the Navier-Stokes equations, which are written by Navier. There is no v. And there is no variation in the x direction. Well, we know that already from never mind, du dx, this profile is not a function of x. Everything on the left is 0. The pressure field through this fluid is uniform, and there is no variation in the x direction. Oh, I forgot to write the term accounting for time dependence, du, the time which belonged here. And what's left as a governing principle is that this partial derivative must be of the same order as the only other term in the equation, which is nu. And then partial of u with respect to y twice. That's the curvature of the velocity profile. Keep in mind, it's just like in thermodynamics. Before you start analyzing anything, define the system, define the entity that you are talking about. The system in this particular example is the fluid layer of thickness delta. And to go from the partial differential equation to the algebraic statement of scale analysis, you must say first, I am referring to the scales of this layer of fluid. And those scales are, meaning changes in u, are of order u, capital U, which is the speed of the wall. Time, that is the object of the game. And then nu, u, and then delta squared. Little delta has the same meaning as in the introduction to today's lecture. It is the distance of a vertical penetration of movement or change in movement due to friction against the wall. And you see from here that this delta is the same as nu times t to power 1/2, which I did not write here, but I should have. That's funny. I meant to continue here with to arrive at the same scale. If you allow me to go back, so what would fit in this little? Let's make a diamond shape here. I'm writing over here. So I'm going back to the beginning of the lecture. In this space, I would take the scale of delta, and then Reynolds number based on L to minus 1/2. And in it, I replace L by time times u infinity. Let's do, first of all, this expression is the same as, my mind is jumping forward too fast. So delta is of order L Reynolds based on L to minus 1/2. That means L and then nu over L u infinity to 1/2. And of course that means L to 1/2. And then nu over u infinity to 1/2. And L to 1/2 is t times u infinity. So that becomes t to 1/2. And you get a delta is, obviously you cancel those two, and you get nu times t to 1/2. That is what I wanted to add at the time when I was talking about Drew, who was observing what's happening at this location. So the time of viscous penetration vertically times the kinematic viscosity and then power 1/2 equals the distance of viscous penetration. And this is why the problem that I unearthed from the history of, they call it hydrodynamics in the 1800s, matches or announce the arrival, if you want, of boundary layer theory. It's important to know that the distance of, in this case, viscous penetration, also known as momentum diffusion, because it happens in this invisible way of one layer rubbing against another layer. Every diffusion mechanism, you'll see very soon the diffusion of heating by conduction in time-dependent fashion brings with it a thermal penetration depth, the formula of which is the same as this, except that the kinematic viscosity is replaced by the thermal diffusivity. So that will be our object very, very soon. The important to retain is the idea that you can describe a flow in its steady state, no question about that. Or if you imagine writing on a packet, you see changes in time. It's just like when you're riding on a train. What you see through the window is changing. But if you fell out of the train and you're stationary, things are a lot simpler. Okay, something else. In case you get the idea that I agree with the state of affairs in academia too much, let me show you something that speaks of critical attitude. I don't know how it was when you took fluid mechanics, but quite often when professors teach this story of boundary layer theory, they do not stress the fact that it begins with the assumption that the layer is slender. So this is quite often not acknowledged as an assumption, but in a hurry, even the textbook presents a sketch of this boundary layer that looks like this. I'm sure you've seen this drawing. Yeah, this drawing is wrong because you see delta of increases as L to power 1/2. And L to power 1/2, for that matter, L to a power smaller than 1, is a curve with a blunt nose. It never goes down, but it's certainly not a sharp knife. You see? This is how you know that the professor is either lazy or not interested. Never mind the fact that this length must be large enough for this boundary layer theory to be valid. Remember, the Reynolds number based on L to 1/2 has to be of order 10 or greater. Never mind. In other words, you may think that I'm picking nits, being nosy about something where the theory is not valid. It's not that. I'm actually very picky about the meaning of the mathematical expression. a mathematical formula in x versus y is the same as making a drawing. In the history of science, first there was the drawing called geometry. And from those very drawings, algebra was invented. Algebra was not invented from somebody's whatever, they dug up some equations from the pyramids. No, they looked at the relationship between little areas on the drawings. This is the work of tell me again his name, algebra. Yes, who wrote his book in Arabic, but he was Persian, okay? Yeah, he knew geometry. In fact, this book is full of drawings before it gets to the equations. So you see, question the authority of those who preach over you.